In this work, we present vMF-Contact, a novel architecture with uncertainty-aware 6-DOF grasp detection framework based on probabilistic contact grasp representation. A contact grasp is defined by a contact point, baseline vector, approach vector, and grasp width. We focus on the probabilistic modeling of this representation, accounting for both aleatoric and epistemic uncertainties. Specifically, we model the likelihood of the baseline vector using the von Mises-Fisher distribution, which is parameterized by the mean direction μc and concentration kappa c, predicted by a shared MLP based on the encoder features EC. A conjugate prior for μc, modeled as another vMF distribution with parameters μ0 and kappa 0, represents prior knowledge about the baseline vector's direction. A reasonable choice of an informative prior direction can be the negative surface normal on the object, considering antipodality for grasping. The evidence MC represents the belief on observed point feature, which is predicted typically by a normalizing flow. To this end, the posterior updates combine prior and likelihood with respective concentrations. For novel contact feature with low evidence, the posterior remains conservative and aligned more with the prior. To learn the posterior parametrizations together with likelihood, we derive the exact Bayesian loss for vMF distribution, as one of our contributions. Notably, previous works modeled the likelihood with power spherical distribution, which can only lead to the closed-form solution, sacrificing analytical tractability for Bayesian inference. Our vMF-Contact architecture consists of the following modules. First, the raw point clouds from a single camera view go through the point net-based backbone, giving the point features ZC. Second, a shared point-wise MLP predicts the grasp parametrizations. Then, a normalizing flow attempts to fit a trainable GMM to the point features, providing evidence predictions MC. Finally, the evidence serves the posterior update with the likelihood from MLP predictions. Moreover, we extend 2D feature reconstruction and evidential deep learning to the point cloud-based reconstruction, improving robustness to input noise and enhancing uncertainty quantification as well as accurate grasp detection. For data collection, synthetic data is generated including point clouds and non-collision grasps for supervision. Notably, the training scenes contain only 12 distinct objects, each with a randomized presence. In real-world experiments, we evaluate on- and distribution objects from our dataset and out-of-distribution unseen items. We validate the effectiveness and generalization capability of vMF-Contact, without any sim-to-real adaptation. Comparable performance is observed across in-distribution and out-of-distribution scenarios, including unseen objects, sensor noise, and varying geometric and physical properties, such as deformable items. Notably, with reconstruction and uncertainty-based grasp selection, our method achieved a 39% improvement in overall clearance rate compared to baseline approaches.